depends on both x and y, and that then maps to 0 or 1. And it's efficiently computable. So imagine that there is an efficient implementation of this. And now here's the protocol. Verifier 0 sends a string of n bits to the prover and a random qubit. And verifier 1 sends a string of n qubits to the prover. And the prover, upon receiving these, he computes the value of f of xy, which is either 0 or 1. And then depending on whether that's 0 or 1, if it's a 1, the qubit psi is routed onwards to verifier 1. And if the function value is 0, the qubit is routed back. And we call this primitive f routing, where f is the function that somehow determines whether it's routed onwards to the verifier 1 or routed backwards to verifier 0. So here let's study the attacking game. So now let's go into the minds of Alice and Bob, and let's see how they would attack this. So Alice receives x and a qubit psi. Bob receives this value y, and there is some state psi AB that they share, some entangled state, and we want to somehow get a bound on how big this state psi is. What they do is they send some density matrix to each other, depending on these inputs. Bob sends density matrix B, Alice sends density matrix A, and then if f of xy is 1, Bob has to be able to output psi from the density matrix sigma A plus whatever he left at home from the entanglement. And Alice, if f of xy is 0, Alice has to be able to output psi. Right? This is the attacking game from Alice and Bob. And what I'm interested in is this notion which I call E of f. So it's the entanglement, the minimum number of qubits of entanglement needed to achieve this feat. That's what I call E of f, and that is sort of if they can do that, then with E of f amount of entanglement, they can break this f routing protocol. Right? But so we're thinking about Alice and Bob here. And so we actually showed a couple of things about this, but first of all, my intuition tells me that if f is somehow needs a lot of memory to be computed. So in complexity theory, we always think about the time that a function takes. So that should be polynomial. So that means efficient. But not only the time, but also the number of memory cells that are needed for the computation is something that comes into play, and that is usually in between logarithmic and polynomial amount. And here I conjecture that the amount of entanglement that is needed for this attacking game for f routing is somehow exponential in the amount of memory that is needed to compute f. And somehow the idea is, the intuition is that before it is known what f of xy is, right? Because Alice has to send this message sigma A to Bob, and Bob has to send sigma B to Alice. And only Bob knows y, he doesn't know x, and Alice doesn't know y, only knows x when she does that. And somehow this qubit psi has to be already on the right side before this function f of xy is known. Otherwise, it can't work. And so it feels that it's related somehow, says my intuition, to the space needed to compute f. And actually, we were able to show the other way around, that if you have little space, if you only need very little space to compute f, then actually the number of entangled bits to somehow attack this f routing game is only polynomial. So if there's logarithmic amount of space, then the number of EPR pairs that are needed is only polynomial. But the question that we still are struggling with, and we don't have an answer, but is there a function in polynomial time? So is it efficiently computable? Not in logarithmic space, so it requires more than logarithmic amount of memory, and such that the entanglement uses for f is more than polynomial. Right? That's what we're after. And if we have that, then we can build a secure position verification protocol. And then it turns out that if you look in the literature and you look at other computer science / crypto problems, similar problems that are seem completely different, but they have a similar flavor to what the problem is here. There also are these sort of logarithmic versus linear versus exponential upper and lower bounds. And here are a few of these instantations. One is called private simultaneous messages. This is something that cryptographers study. Another one is, and I will talk a bit about this, conditional disclosure of secrets. Secret sharing protocols is something that has a similar flavor. And in all these settings, the best upper bound that we know in whatever is measured there is exponential, just like we have for our F routing, and the best lower bounds are linear. And so there's a huge gap there also. Okay, so then this was where things stood, and then these guys from this ADS CFT correspondence got interested in this. And for those of you who don't know what that is, that's the following. That's something completely different. And that is a tool, actually, to study quantum gravity. And on one end of the ADS CFT, you have the anti-de Sitter space, which you can think of as a three-dimensional space where somehow you have a nice theory of gravity. So it's a model of space-time that used in theories of gravity. And on the other hand, you have a two-dimensional space called conformal field theory, and this is one dimension smaller than this one. And somehow what this ADS CFT correspondence says is that, well, this one has quantum field theory invariant under conformal transformations. And this correspondence somehow says that whatever happens in this three-dimensional picture, there is a corresponding action on this two-dimensional conformal field theory. And somehow this is very interesting. Yeah, so everything that can happen here on in the bulk, so that happens somehow inside this little cylinder, that has somehow a corresponding explanation on the boundary of that cylinder called the conformal field theory. And this is used, this correspondence tool, to study quantum gravity, but also to study black hole physics like quantum chromodynamics and even condensed matter physics. So this is a very interesting and very often used tool in this community. And so you might wonder, what has this to do with the story that I've been talking about? And here's this connection that was uncovered by May, Dolev, and Cree a couple of years back. And so here we have the correspondence back. And now, if you stare a little bit at this ADS-C bulk thing, where you have somehow actions coming from the bulk, from the boundary, somehow sending something inside to the bulk, and that sends some information back to the boundary. If you squint your eyes a little bit, you can actually view this as a honest QPV protocol, where we have the verifier sitting at these boundaries, and there's somehow an honest prover inside the bulk, and somehow messages are sent to the prover, like the F routing protocol, and then the answers are sent back outside again. Right? So this could be a model of a honest QPV protocol. And now this correspondence, if you look at the boundary, it actually turns out to be an attack on this protocol. And it's maybe not entirely clear, but somehow whatever this action, this three-dimensional action, if you somehow do it in this two-dimensional boundary, it becomes an attack of this protocol. And this attack is actually efficient also, according to the correspondence people. So they say that this correspondence implies that there actually is a linear upper bound on the amount of entanglement that's needed for these attacks. So that's actually very much in contradiction to my own intuition about these things. And furthermore, it means that if F is in P, then there is an efficient entanglement attack to all these position verification protocols, provided that this correspondence is correct. However, there's no construction for how actions in the bulk translate to the boundary. There's only a conjecture that this is the case. There's some assumptions and unproven conjectures, and somehow there's no construction that convinces me that this is true. But nevertheless, it's sort of very interesting to look at this, and we sort of got engaged with the ADS-CFT people. And then I sort of